Jet disruption by plasma is another possibility. If the plasma environment surrounding the nucleus is dense or uneven, jets emerging from the nucleus could lose coherence as they interact with charged particles. This could result in diffuse rather than collimated jets, reducing their visibility in high-resolution instruments. At the same time, long-exposure amateur observations may detect faint brightness variations caused by underlying jet dynamics. Dust grain size further complicates interpretations. Large grains dominate the coma of 3I Atlas, and these grains respond differently to jets than smaller particles. Fine particles align closely with gas flow and produce sharp, narrow jets. Large grains follow more ballistic or gravitationally influenced paths, producing broader and more diffuse structures. If most dust in 3I Atlas consists of large aggregates, jets would appear wider, less structured, and harder to resolve, especially in instruments with limited exposure times. Spin axis orientation also affects visibility. If the rotation axis points roughly toward Earth or Mars during observations, the projected rotational motion may appear minimal. This can suppress periodic brightness variations and obscure rotational signatures. Such geometry could also create projection effects that mimic rings or arcs, accentuating the visibility paradox. Despite these challenges, several methodological approaches can help constrain the rotation state. High-cadence photometry across multiple nights can reveal repeating brightness patterns, even if amplitudes are small. Polarimetric monitoring can track changes in dust alignment influenced by rotation. Infrared observations can detect thermal hotspots corresponding to active regions. Spectroscopy can reveal periodic variations in gas production if jets rotate into and out of the line of sight. Modeling of dust morphology can connect coma features to rotational parameters. So far, none of these methods have produced consistent periodicity, but additional data during solar storm-induced coma changes may help. If plasma density decreases or optical depth temporarily drops, structures related to rotation may become more visible. The rotation state of 3I Atlas also has implications for its long-term evolution. Rapid spin changes can destabilize the nucleus or alter the direction of the object's non-gravitational acceleration. In extreme cases, high rotation rates can lead to mass shedding or fragmentation events. While no evidence currently suggests that 3I Atlas is at risk of structural failure, monitoring for sudden brightness increases or changes in dust production remains important. In summary, rotation, jet dynamics, and internal structure contribute significantly to the object's observed behavior. Although the rotation state remains unresolved, natural explanations based on complex outgassing patterns, large-grain dust environments, plasma interactions, and geometric effects account for the available data. Continued monitoring across multiple wavelengths, especially during periods of changing solar wind conditions, will be critical for determining whether the rotation state stabilizes or remains irregular. To understand the ongoing evolution of 3I Atlas, it is necessary to examine how temperature, illumination, and the object's internal structure interact as it approaches perihelion. The thermal environment of a comet or comet-like body determines which volatiles sublimate, how quickly mass is lost, and how dust and gas are released into the coma. For 3I Atlas, these processes are especially important because the object's high CO2 abundance, suspected organic-rich crust, and uncertain rotation state create a complex and potentially unstable thermal configuration. The thermal model begins with the object's energy balance. Sunlight absorbed at the surface is re-radiated into space and converted into sublimation energy. The efficiency of these processes depends on albedo, surface composition, thermal inertia, and porosity. If 3I Atlas has a dark radiation-processed crust, as suggested by polarization, data, its albedo may be low, allowing it to absorb a significant fraction of solar radiation. This increases surface temperatures and enhances sublimation of more volatile ices such as CO2 and CO, even at large heliocentric distances. Thermal inertia. The ability of a material to store heat also influences sublimation. Low thermal inertia results in rapid heating and cooling, with strong diurnal temperature variations. High thermal inertia causes more gradual temperature changes and deeper heat penetration into subsurface layers. For an object that has traveled through interstellar space for millions of years, thermal inertia may be dominated by a thick porous crust composed of complex organics and dust aggregates, reducing heat flow into deeper icy layers. This configuration can produce a layered sublimation profile. In the upper layers, CO2 ice sublimates readily when heated. Water ice, insulated beneath the crust, may remain inactive until the object approaches much closer to the Sun. This matches the observed composition: strong CO2 emissions and comparatively weak H2O production. Seasonal effects also play an important role. If the rotation axis of 3I Atlas is significantly tilted relative to its orbital plane, one hemisphere may experience prolonged sunlight while the opposite hemisphere remains shadowed. In such cases, the distribution of active areas becomes highly asymmetric. This can influence the direction of jets, dust morphology, and non-gravitational acceleration. If the object is in a complex rotation state or tumbling, sunlight may reach different surface regions unpredictably, modifying activity patterns from one rotation cycle to the next. This can cause irregular jet-driven acceleration, inconsistent coma features, and intermittent brightness variations. Combined with plasma interactions, these fluctuations may contribute to the visibility paradox. Approaching perihelion introduces additional complexities. The increasing solar flux raises surface temperatures, causing sublimation rates to rise non-linearly. For CO2-driven comets, activity may peak earlier than for water-driven comets, with a steep increase as the object crosses certain thermal thresholds. If deeper layers contain water ice beneath the insulating crust, water-driven activity may begin closer to the Sun, potentially triggering new jets or structural changes in the coma. However, if the surface crust remains intact, deeper layers might never reach water sublimation temperatures before the object departs the inner solar system. In such a scenario, 3I Atlas would remain CO2 dominated throughout its entire apparition. Thermal models also predict the potential for near-perihelion outbursts. These events occur when subsurface pressure builds beneath the crust and eventually ruptures, releasing large amounts of gas and dust suddenly. Outbursts can dramatically increase brightness and alter the coma geometry. For an object with a heavily processed surface layer, narrow fractures or weak points could produce localized explosive events. Observing whether 3I Atlas undergoes such activity will help clarify surface structure and volatile distribution. Another factor is the thermal wave. Heat does not penetrate deeply into cometary nuclei. Typical depths range from centimeters to meters, depending on material properties. For interstellar objects exposed to cosmic rays for long periods, the outermost layers may be structurally weak or porous. This could influence how heat diffuses inward and how quickly volatile reservoirs activate. The interplay of thermal gradients, rotation, and internal layering complicates predictions of perihelion behavior. Several possible outcomes can be considered. Scenario 1. CO2 continues to dominate activity throughout perihelion. If the crust remains intact, water never sublimates in significant quantities. Activity remains relatively stable, governed mostly by CO2. In this case, dust production continues to be dominated by large particles, and coma features remain diffuse. Scenario 2. Water-driven activity initiates near perihelion. If the thermal wave penetrates the crust or fractures open new vents, water sublimation may begin. This can increase mass loss rates, produce finer dust, and create sharper jets. Such changes may make internal structure more visible if optical depth decreases. Scenario 3. Outbursts occur due to trapped volatiles. Pressure buildup beneath the crust could lead to episodic releases. Outbursts increase brightness temporarily, produce expanding dust shells, and may shift the object's spin state or acceleration. These events could temporarily reveal structural detail before the coma redensifies. Scenario 4. Structural fragmentation. While there is no evidence suggesting imminent fragmentation, comets with significant internal stresses or rapid spin changes can break apart near perihelion. This possibility is low, but cannot be excluded until more rotational data become available. The thermal model also influences how the object interacts with the solar wind. Increased sublimation releases more neutral molecules that become ionized, increasing plasma density. A denser plasma environment enhances scattering and may worsen visibility in high-resolution imaging. Conversely, if the solar storm disrupts the plasma density, internal features may become more visible even as activity increases. Thermal predictions also connect directly to dust dynamics. As gas flow intensifies near perihelion, dust grains of different sizes respond differently. Fine grains accelerate strongly with gas flow and can produce narrow jets. Large grains follow ballistic trajectories and contribute to broad, structureless coma components. If fine-grain production increases near perihelion, visibility of jets may improve. Forecasting perihelion behavior requires integrating multiple data sets, rotational models, compositional data, thermal inertia assumptions, and observations of dust production. At present, the most likely scenario is continued CO2-dominated activity, possibly accompanied by increased dust output. Water sublimation remains uncertain and depends heavily on crust integrity. Regardless of which scenario unfolds, perihelion represents a critical observational window. The object will experience rapid changes in temperature, solar radiation, and plasma environment. Monitoring across infrared, ultraviolet, and visible wavelengths will provide essential data for refining thermal and compositional models. In summary, the thermal behavior of 3I Atlas reflects a complex interplay between volatile composition, surface layering, rotation, illumination geometry, and possible plasma interactions. Predicting perihelion activity requires considering both the unique properties of the object and broader physical principles governing sublimation and heat transfer. Continued observations near perihelion will help determine whether deeper volatiles activate, whether outbursts occur, and how these events influence coma morphology and visibility. As 3I Atlas approaches regions of stronger solar influence, the interaction between its outflowing material and the solar wind becomes a dominant factor shaping its appearance. These interactions determine the structure of both the dust tail and the ion tail, influence the dynamics of the surrounding plasma, and contribute to several of the observational anomalies described earlier. The solar wind consists primarily of protons, electrons, and alpha particles traveling outward from the Sun at velocities typically between 300 and 800 km/s. Embedded within this flow is the heliospheric magnetic field, a large-scale spiraling magnetic structure shaped by the Sun's rotation. When the solar wind encounters the neutral gas escaping from a comet-like object, a series of predictable plasma processes begin. The first major step is photoionization. Ultraviolet radiation from the Sun ionizes neutral molecules, converting them into charged particles. Water, carbon dioxide, carbon monoxide, and other volatiles all have specific ionization cross-sections that determine how efficiently they become ionized. Once ionized, these particles are rapidly swept into the solar wind flow. The second step is charge exchange. A solar wind proton can capture an electron from a neutral atom or molecule, producing a fast neutral particle and a slow-moving ion. Charge exchange is a key mechanism in generating the extended hydrogen envelopes observed around active comets. For 3I Atlas, the detection of hydrogen emissions in ultraviolet wavelengths is consistent with both photoionization and charge exchange processes. These ionized particles then respond to the magnetic field embedded in the solar wind. The newly created ions spiral around magnetic field lines, forming the ion tail, which is typically narrow, blue in visible light, and aligned directly opposite the Sun. The dust tail, by contrast, consists of neutral particles influenced primarily by radiation pressure and gravity, producing a broader and often curved structure. For 3I Atlas, several observations suggest that its interaction with the solar wind is unusually strong. The object's high CO2 abundance means a substantial portion of its outgassing consists of molecules that ionize efficiently and produce high densities of CO2+ and CO+ ions. These ions interact strongly with the solar wind, creating a dense plasma environment. Such a plasma-rich environment can produce effects that influence visibility. Increased scattering of sunlight, suppression of fine jet structure, broader brightness profiles, and variable contrast across the coma. Additionally, the interaction region between the outflowing ions and the solar wind can produce magnetic draping, a phenomenon where the heliospheric magnetic field lines wrap around the object. Draping can influence the shape of the ion tail and create boundary layers within the coma where plasma density and magnetic field strength change abruptly. Magnetic draping also contributes to a phenomenon known as field line rotation, where local magnetic structures twist as they interact with the outflow. If the dust or plasma density is sufficiently high, these rotations can produce asymmetric patterns or sudden shifts in tail orientation. For 3I Atlas, these interactions may be further complicated by its suspected dense plasma envelope. If plasma accumulates near the nucleus, instead of being rapidly carried away, the local environment can become highly structured. Such structures may include regions of enhanced electron density, transient magnetic reconnection sites, turbulence-driven density waves, and irregular plasma boundaries. These effects can influence observations across wavelengths. For example, in visible light, a dense plasma region may scatter photons and produce a smooth, featureless glow. In ultraviolet wavelengths, the same region may appear bright due to ion emissions. In radio frequencies, plasma density gradients can cause dispersion or phase shifts. Tail morphology provides additional clues. Some amateur images have reported irregularities in the dust tail, including subtle discontinuities or apparent kinks. While such structures can arise from jets or rotations, they can also result from solar wind pressure fluctuations. If the solar wind momentarily increases in density or changes direction, the dust tail can be deflected or compressed. This effect may become more pronounced as the solar storm approaches. The ion tail may exhibit even more dramatic responses. Ion tails are sensitive to both the magnetic field direction and the flow speed of the solar wind. During periods of stable solar wind, the tail remains smooth and well aligned. During disturbed conditions, such as when a coronal mass ejection arrives, the ion tail can undergo rapid disconnection events, abrupt directional changes, temporary broadening, or segmenting into multiple filaments. Disconnection events occur when the magnetic field embedded in the solar wind reconnects with magnetic structures formed in the comet's coma. When this reconnection takes place, the existing ion tail detaches and drifts away while a new tail forms. These events have been observed in many comets, including 2P Encke and C2006 P1 McNaught. If 3I Atlas has a dense or irregular plasma environment, disconnection events may occur more frequently or produce atypical signatures. Ion dynamics may also contribute to the visibility paradox. If the inner coma is dominated by dense plasma, photons may scatter multiple times before reaching observers, suppressing structural detail. At the same time, the ion tail may appear sharp and structured when observed at large distances from the nucleus, where plasma density decreases. This contrast can create the impression that the object has hidden its internal structure even while exhibiting sharp features farther out. Another possible contributor is pickup ion instabilities. When neutral particles become ionized, the resulting ions may not immediately adopt the velocity of the solar wind. Instead, they form ring distributions in velocity space, which can lead to wave instabilities and plasma turbulence. Such turbulence can alter the morphology of the coma by producing density waves, filamentary structures, or transient bright regions. Depending on wavelength, these effects may appear as rings, arcs, or fuzzy edges. As the solar storm approaches, these plasma interactions are expected to intensify. Increased magnetic field strength and solar wind pressure can amplify turbulence, drive stronger reconnection, and increase ionization rates. This can lead to rapid changes in the appearance of both tails and the coma. Monitoring these patterns across multiple wavelengths will help determine whether the plasma shield hypothesis adequately explains the visibility paradox. If plasma density drops sharply during the storm and the nucleus becomes visible, this would support the idea that a dense plasma environment has been obscuring internal structure. If visibility decreases further, plasma scattering may be even more significant than current estimates suggest. Dust and ion dynamics also affect the long-term evolution of the object. Persistent plasma interactions can modify the shape and extent of the coma, influence dust trajectories, and affect non-gravitational acceleration. As 3I Atlas continues its passage through the inner solar system, these interactions will play a central role in shaping its observable behavior. In summary, solar-wind interaction provides a coherent physical framework for many of the features observed in 3I Atlas. The combined effects of photoionization, charge exchange, magnetic draping, turbulence, and tail dynamics create a complex, evolving system. Understanding these processes is essential for interpreting the object's unusual visibility and for predicting how it will behave as it approaches perihelion and encounters changing solar wind conditions. As 3I Atlas moves deeper into the inner solar system, the intensity of solar radiation increases rapidly. This growing radiation flux affects every component of the object: its volatiles, dust grains, plasma environment, ion tail, and emission spectra. A comprehensive interpretation requires understanding how radiation interacts with escaping molecules and how these interactions generate the observable signatures across ultraviolet, optical, infrared, and radio wavelengths. The starting point is solar ultraviolet radiation, which is responsible for ionizing neutral molecules released from the nucleus. Each volatile species has a characteristic ionization cross-section and lifetime. Water molecules typically survive for several thousand seconds before ionizing, while carbon dioxide and carbon monoxide have different lifetimes depending on solar activity. As the object approaches the Sun, these lifetimes decrease, increasing the ionization fraction within the coma. This effect has direct consequences for the density of the plasma environment surrounding 3I Atlas. If the object is strongly CO2 active, as spectroscopic data indicate, then large quantities of CO2 plus and CO plus ions accumulate near the nucleus. These ions have distinct emission features, especially in ultraviolet wavelengths. Observations by MAVEN and Earth-based ultraviolet telescopes have already detected enhanced CO2 plus emissions, reinforcing the conclusion that carbon dioxide sublimation is the dominant process. Another key factor involves photodissociation, the breakup of molecules under ultraviolet radiation. Water photodissociation produces hydrogen and hydroxyl, OH. These fragments create measurable signatures in ultraviolet and radio wavelengths. Hydroxyl emissions, in particular, form one of the most widely used traces of water production in comets. For 3I Atlas, O detections remain weaker than expected, consistent with its low water abundance. This disparity between CO2-driven activity and H2O-driven activity is one of the clearest compositional indicators distinguishing the object from solar system comets. Radiation also influences dust grains. Absorption of ultraviolet and visible light heats dust particles, altering their temperature and re-radiation profile. Large grains, which dominate the coma of 3I Atlas, heat and cool more slowly than fine grains. Their thermal emission becomes significant in the mid-infrared, where instruments like JWST can detect spectral features associated with silicates, organics, or mixed grain compositions. Preliminary infrared data indicate an abundance of complex organics in the dust. These organics are consistent with long-term cosmic ray processing and support the interpretation that the object formed in a cold, distant environment rich in volatile ices. The radiation environment also shapes the ion tail. Newly ionized particles are accelerated by the solar wind electric field, forming a stream of ions that aligns with the direction of the interplanetary magnetic field. This tail can extend millions of kilometers and exhibits rapid variability depending on solar wind conditions. Ion chemistry within the tail provides clues about the composition and activity level of the nucleus. CO2 plus and CO plus emissions, for example, can be mapped to determine the degree of ionization and distribution of parent molecules. If CO2 outgassing increases near perihelion, these emissions should strengthen and expand. If the plasma environment is dense near the nucleus, ions may undergo additional interactions such as charge exchange or recombination, altering the relative intensities of spectral lines. Understanding these processes requires multi-wavelength diagnostics, with each region of the electromagnetic spectrum providing different types of information. Ultraviolet, UV. Observations. UV measurements detect emissions from ionized species such as CO2+, CO+, and OH. These emissions provide direct information about ionization rates and volatile composition. The presence of strong CO2+ lines and comparatively weak OH lines confirms the dominance of CO2 outgassing. Visible light observations. Visible imaging reveals dust distribution, coma morphology, and overall brightness. Forward scattering geometry can significantly enhance brightness in this wavelength range. Visible observations also provide photometric data for rotational analysis, although interpretation remains complicated for 3I Atlas due to coma density and potential tumbling. Infrared, IR, observations. Infrared spectroscopy identifies molecular vibrational bands, allowing researchers to quantify water, CO2, CO, and other volatiles. Infrared observations also characterize dust temperature, grain size distribution, and organic content. JWST data for 3I Atlas indicates strong CO2 bands and weaker water bands, reinforcing the compositional anomalies observed at other wavelengths. Radio observations. Radio telescopes detect transitions associated with hydroxyl and other molecules. These signals provide additional constraints on water production. Radio data for 3I Atlas show only weak OH emissions, consistent with low H2O abundance. Radio wavelengths can also probe plasma density through dispersion effects. Together, these multi-wavelength observations form a coherent picture. 3I Atlas is heavily dominated by carbon dioxide-driven activity, contains large and complex dust grains, and exists within a dynamic and possibly dense plasma environment. Radiation also influences the large-scale structure of the coma through fluorescence excitation. When molecules absorb ultraviolet photons and re-emit them at specific wavelengths, they create characteristic spectral lines. These fluorescence emissions can help quantify the relative abundance of different volatiles. In the case of 3I Atlas, fluorescence models show that CO2 fluorescence dominates by a wide margin over water fluorescence. The radiation environment also interacts with dust in ways that can modify the visibility paradox. Radiation pressure pushes dust grains away from the sun, shaping the dust tail and influencing the distribution of particles within the coma. Large grains respond weakly to radiation pressure, remaining near the nucleus for longer periods. This contributes to a dense, broad coma in the inner region, potentially increasing optical depth and reducing visibility of internal structures. Another effect is charging of dust grains. Ultraviolet radiation and interactions with the surrounding plasma can deposit electric charge onto dust grains. Charged grains behave differently than neutral ones, responding to electromagnetic forces. This can alter their trajectories and make dust alignments sensitive to magnetic fields. Charged grains may also interact differently with polarized light, affecting polarization signatures. Charged dust and ions together can produce microscale plasma instabilities. These instabilities can generate wave structures, density fluctuations, or localized turbulence within the coma. Depending on wavelength, instabilities may appear as faint arcs, filaments, or diffuse patches features, occasionally reported in amateur images. Radiation also drives the evolution of the tail chemistry. As the object gets closer to the Sun, ionization rates increase, boosting production of key species that serve as diagnostics for activity level. For example, higher CO2 plus densities should strengthen ultraviolet tail emissions. Increased production of CO may enhance CO plus lines. If water activity increases near perihelion, OH emissions will become more prominent. Monitoring these changes provides insight into whether deeper ice layers begin sublimating or whether CO2 remains the dominant volatile throughout the perihelion phase. In summary, the radiation environment plays a central role in shaping the chemical, physical, and plasma characteristics of 3I Atlas. Ionization processes, photodissociation, fluorescence, dust charging, and radiative heating all interact with the object's unique composition and dust environment. Multi-wavelength observations across ultraviolet, visible, infrared, and radio bands provide essential constraints for interpreting the object's behavior and resolving anomalies such as the visibility paradox. As the predicted coronal mass ejection, CME, approaches 3I Atlas, its effects on the object's plasma environment, dust dynamics, and visibility become increasingly important. A CME represents a large-scale solar disturbance consisting of magnetized plasma moving at hundreds to more than 1,000 kilometers per second. When a CME interacts with an active comet-like object, it can trigger a series of rapid and observable changes. The first and most immediate effect is plasma compression. As the CME's high-density plasma front encounters the neutral gas and ions in the coma, it compresses the plasma around the nucleus. Compression increases electron density, strengthens magnetic fields locally, and raises the effective optical depth near the object. Depending on the initial state of the plasma environment, this compression can either reveal or obscure structural features. If the coma of 3I Atlas contains a dense but uneven plasma envelope, compression may equalize density gradients, momentarily reducing scattering and increasing visibility. Conversely, if the CME enhances existing scattering processes, structural features may become even more diffuse, reinforcing the visibility paradox. The second major effect involves magnetic field reconfiguration. CMEs carry their own embedded magnetic fields, which can differ significantly from the background interplanetary magnetic field. When these magnetic fields interact with the plasma surrounding a comet, they can create conditions for magnetic reconnection. Reconnection rapidly releases energy and can reorganize plasma flows near the nucleus. This is the mechanism behind cometary ion-tail disconnection events. For 3I Atlas, whose plasma environment may already be highly structured, magnetic reconnection triggered by the CME could produce abrupt changes in the ion tail. Possible signatures include a sudden break or gap in the tail, rapid reorientation of the tail direction, transient brightening of tail segments, or the formation of multiple ion filaments. These changes may occur within minutes to hours after CME impact and can be detected in both amateur and professional observations. The third effect concerns ionization rate enhancement. CMEs often contain energetic particles that increase ionization rates in the coma. When more neutral molecules become ionized, the plasma environment thickens. For a CO2-dominated object like 3I Atlas, higher ionization rates may produce stronger CO2 plus and CO plus emissions. This could momentarily increase ultraviolet brightness and alter the spatial distribution of ion-dominated regions. However, a rapid rise in ion density can also amplify scattering, potentially worsening the visibility of jets or inner coma structures in visible light. The competing effects enhanced emission but reduced structural clarity must be interpreted through multi-wavelength observations. The fourth effect involves dynamic pressure variations. The CME's plasma front carries momentum that can push against the coma, altering its shape and size. The outer coma may compress, while the inner coma may expand as sublimation rates increase due to solar wind heating. These distortions can create asymmetries or distortions in the dust distribution. If the nucleus has active jets, the interaction may enhance or suppress specific jets depending on how the CME interacts with local outflow directions. Another possible response is gas sheath detachment, where layers of ionized gas peel away from the nucleus region and flow downstream. Detached plasma layers can appear as faint, expanding shells or arcs when imaged under certain geometries. The CME's arrival could also influence the dust tail. While dust is largely unaffected by magnetic fields, increased solar wind pressure can bend the dust tail more sharply or modify its curvature. Large grains, which dominate the coma of 3I Atlas, respond only weakly, but smaller particles produced near perihelion may show more pronounced deflection. A critical diagnostic opportunity arises from time-structured monitoring. Because the CME is expected around a known window, observers can compare images taken just before impact, during peak interaction, and after the disturbance passes. This three-phase comparison provides an unusually controlled environment for studying plasma dynamics. One key observational outcome would be the temporary emergence of structural features that were previously obscured. If plasma density drops due to reconnection or compression-driven clearing, hidden jets or inner coma details may briefly become visible. On the other hand, if the CME increases plasma scattering, the object may appear even more uniform and featureless. For this reason, the CME impact represents one of the most important opportunities for resolving the visibility paradox. Another set of diagnostics involves spectroscopy during the CME. Increased ionization should strengthen ultraviolet emission lines associated with CO2+, CO+, and OI, atomic oxygen. Enhanced emissions would confirm that CME-driven ionization is affecting the coma. If these emissions increase without a corresponding rise in visible structure resolution, it would reinforce the case that visibility is limited primarily by scattering rather than lack of internal structure. Radio observations also become more informative during CME interactions. CMEs can alter plasma dispersion characteristics, shifting radio line profiles and providing indirect measurements of electron density. If the plasma surrounding 3I Atlas is dense, the CME may produce measurable dispersion effects, offering rare insight into the plasma environment near an interstellar comet. Infrared observations are also valuable. If the CME increases sublimation rates by compressing or heating the coma, CO2 and CO vibrational bands in the infrared may strengthen temporarily. Observing these changes would help quantify the sensitivity of the object's activity to external forcing. As the CME passes, the plasma environment should relax gradually. The ion tail may reform, with the new tail orientation reflecting the changing magnetic field structure. If disconnection events occur, the detached portion of the tail may be visible for several hours or more before dissipating into the solar wind. All these processes highlight a central theme. The physical state of 3I Atlas is not determined solely by its composition and internal properties, but also by its interaction with dynamic solar wind conditions. For this reason, the CME event is not merely a disturbance, but a natural experiment offering insight into coma structure, plasma density, tail chemistry, and scattering behavior. In summary, a CME encounter offers multiple diagnostic opportunities: plasma compression that alters optical depth, magnetic reconnection that reshapes the ion tail, enhanced ionization that strengthens spectral emissions, dynamic pressure changes that deform coma geometry, potential temporary improvement or degradation in visibility, and multi-wavelength signatures that help confirm physical mechanisms. Whichever scenario occurs, the event will serve as an important test for evaluating the plasma shield hypothesis, radiative transfer interpretations, and the physical behavior of a CO2-dominated interstellar object encountering a major solar disturbance. After a major CME passes over an active comet-like object, the surrounding plasma environment, dust distribution, and internal sublimation processes often undergo measurable changes. For 3I Atlas, these post-CME effects are especially significant because of the object's unusual dust composition, CO2-dominated outgassing, and potential insulating crust. The period immediately following the CME offers insight into how the object responds to rapid changes in solar wind pressure, ionization rates, and magnetic field conditions. A primary area of interest is the possibility of activity enhancement. CMEs increase local temperatures within the coma by compressing plasma and increasing the flux of energetic particles. This additional energy can accelerate sublimation rates, particularly for more volatile species such as carbon dioxide and carbon monoxide. If the thermal wave penetrates the upper layers of the nucleus more deeply, new sublimation pathways may open, activating regions that were previously dormant. For 3I Atlas, enhanced CO2 sublimation would increase gas production and accelerate dust ejection. because the object appears to release predominantly large dust grains. A rise in outgassing may produce a more massive but still coarse-grained dust outflow. This would expand the coma and increase its brightness while maintaining the smooth, low-contrast appearance already observed. Another potential consequence is pressure-driven outbursts. If volatiles accumulate beneath a rigid or semi-rigid organic crust, a sudden rise in internal pressure could trigger a surface rupture. Outbursts of this kind are well documented in solar system comets and typically release large amounts of gas and dust in a short period. The plume resulting from an outburst expands rapidly and can create concentric dust arcs, shell-like structures, or a broad fan-shaped brightening. These features may appear temporarily in visible images before being dispersed by solar radiation pressure and plasma interactions. For 3I Atlas, an outburst triggered by CME-induced heating would be especially informative. If the outburst increases the proportion of finer dust particles in the coma, it could temporarily improve structural visibility. Finer grains scatter light differently and may reveal jets or morphological features obscured by the predominance of large aggregates. Conversely, if the outburst releases primarily large grains, coma opacity may increase further. The behavior of large dust grains after a CME also warrants analysis. Large grains respond primarily to gravity and the initial outflow velocity rather than to solar radiation pressure. This means they tend to follow ballistic trajectories and remain near the nucleus for extended periods. A sudden increase in dust production could create a dense inner region, raising the optical depth and reducing visibility of the nucleus further. However, increased solar wind pressure after a CME may accelerate plasma drag on charged dust grains, altering their motion. If dust grains accumulate electric charge due to ultraviolet radiation and surrounding plasma, their trajectories may become sensitive to electromagnetic forces. This could create subtle asymmetries or diffuse streaks in the coma, depending on the direction of the magnetic field. Another concern following a CME is structural stress within the nucleus. Uneven heating, asymmetric sublimation, and rotational torques can produce internal strain. For a small nucleus, rapid changes in mass distribution may alter the spin state. If 3I Atlas is in a tumbling or near tumbling state, additional torques could destabilize its rotation further. In extreme cases, this can lead to partial fragmentation. Fragmentation events can range from minor shedding of surface layers to the separation of large structural components. Smaller fragments may sublimate rapidly and contribute additional dust to the coma. Larger fragments can produce secondary coma and tails. While no evidence currently indicates imminent fragmentation, the combination of CO2-driven activity, potential crustal tension, and CME-induced stress makes the scenario one to monitor. If fragmentation were to occur, it would provide insight into the internal structure of the nucleus, whether it is monolithic, layered, or loosely aggregated. Interstellar objects may have undergone extensive radiation processing that alters their mechanical properties, making them either more brittle or more consolidated than typical solar system comets. Post-CME evolution also depends on how quickly the plasma environment relaxes. After the CME passes, the surrounding plasma density may drop rapidly or gradually, depending on solar wind conditions. If plasma density decreases sharply, scattering effects may lessen, potentially revealing structural features that were previously obscured. On the other hand, if dense dust persists near the nucleus, visibility may remain limited regardless of plasma conditions. Multi-wavelength observations will be crucial during this period. If ultraviolet emissions decrease after the CME, this indicates reduced ionization rates. Infrared observations may show changes in thermal emission from dust as the coma re-equilibrates. Visible light observations can capture morphological changes, while radio measurements may detect dispersion shifts that signal evolving plasma density. Repeated imaging across several days will help determine whether observed changes represent transient CME effects or longer-term modifications to the object's activity. For example, a temporary brightness increase followed by rapid decline suggests an outburst. A persistent increase in CO2 emissions suggests new active regions were exposed. A change in coma symmetry suggests rotational adjustments or structural shifts. A sudden realignment or regeneration of the ion tail confirms magnetic reconfiguration. Post-CME behavior may also reveal whether the visibility paradox is primarily environmental or intrinsic. If the nucleus or jets emerge after plasma density decreases, this supports the plasma scattering interpretation. If visibility remains unchanged despite reduced plasma interference, the coma may be inherently dense with large grains, or internal activity may be too weak to produce structured features. Additionally, the CME event may offer a unique opportunity to constrain the nucleus size. If the coma temporarily thins, or if an outburst exposes portions of the nucleus, even indirect observations could help refine size estimates. Brightness modeling following sudden changes may provide improved constraints on albedo and effective radius. Large-scale structural evolution is also possible. Some comets develop asymmetric dust fans, spirals, or layered arcs over time as the nucleus rotates and dust production varies. If 3I Atlas possesses similar activity patterns, these structures may become visible as dust distribution adapts to post-CME conditions. In summary, the period following the CME impact offers several key diagnostic opportunities. Observation of possible outbursts driven by thermal or pressure instabilities, detection of temporary improvements or deterioration in coma visibility, monitoring for structural fragmentation or rotational changes, analysis of dust dynamics as the plasma environment relaxes, and multi-wavelength tracking of changes in ionization, tail morphology, and thermal emissions. Regardless of the specific outcomes, this phase will help clarify whether the visibility paradox arises from plasma scattering, coarse dust dominance, rotational effects, or a combination of factors. The CME event functions as a natural experiment, enabling researchers to disentangle overlapping contributions to the object's unusual observational profile. As 3I Atlas approaches perihelion and interacts with increasingly intense solar radiation, its physical behavior becomes more dynamic. However, the most informative phase may occur after perihelion, when the object begins moving away from the Sun. During this period, changes in temperature, sublimation rates, plasma conditions, and dust dynamics can reveal fundamental details about the object's structure, composition, and long-term evolution. A central consideration is how the thermal wave propagates through the nucleus. While heat does not penetrate deeply into comet nuclei, the degree of penetration depends on thermal inertia, porosity, and composition. If 3I Atlas possesses a thick organic crust formed through prolonged cosmic ray processing, this crust may act as an insulating layer. As the object recedes from the Sun, the surface cools rapidly, causing CO2 sublimation to decrease. However, deeper layers warmed during perihelion may continue releasing volatiles for a period, producing delayed activity. This post-perihelion asymmetry is common among comets. Some exhibit stronger activity after perihelion than before, depending on how deeply the thermal wave reaches. For a CO2-dominated object like 3I Atlas, post-perihelion behavior may reflect a shift in volatile dominance. If deeper reservoirs of CO or even water ice begin sublimating after sustained heating, the composition of the coma may change subtly. Another key factor is dust release dynamics. Large grains remain near the nucleus for extended periods, contributing to a persistent coma even as activity declines. If the coma remains optically thick, visibility of internal structures may continue to be limited post-perihelion. However, if fine-grain production increases near perihelion and then decreases afterward, the dust grain size distribution may shift toward larger fragments, producing a broader but dimmer coma. This dust evolution can also influence the object's brightness curve. A slow decline in brightness after perihelion suggests a thick dust environment, while a rapid decline indicates reduced dust retention. Monitoring these brightness profiles will help researchers refine estimates of grain size, dust mass, and sublimation efficiency. The plasma environment will also evolve. As solar flux decreases, ionization rates decline, reducing plasma density. If the plasma shield hypothesis is correct, a noticeable reduction in scattering should occur, potentially allowing high-resolution instruments to observe more structure. Conversely, if the coma density remains high due to large grain retention, visibility may remain limited. Post-perihelion observations may reveal whether the visibility paradox is driven primarily by plasma, dust, or a combination of both. If internal structure remains hidden even as plasma density declines, dust opacity may be the dominant factor. If visibility improves dramatically, plasma scattering may be central. The object's rotation state may also evolve as outgassing decreases. If asymmetric jets exerted significant torque before perihelion, the rotation rate or tumbling state may begin to stabilize. This stabilization could make rotational periodicity easier to detect. Alternatively, If outgassing patterns shift due to deep layer activation or crustal changes, rotational torques may persist longer. Understanding the rotation state is critical because rotation influences potential structural stability. While fragmentation remains unlikely, monitoring for sudden brightness spikes, new jets, or irregular tail patterns will help determine whether internal stresses accumulate as activity decreases. Another important aspect is the object's orbital trajectory. As an interstellar object, 3I Atlas will continue on a hyperbolic path out of the solar system after perihelion. Non-gravitational acceleration driven by sublimation may alter the precise trajectory slightly. By measuring these deviations accurately, researchers can refine estimates of mass, volatile distribution, and directional jet forces. Once the object leaves the inner solar system, its activity will diminish rapidly. At distances beyond several astronomical units, CO2 sublimation becomes negligible. Dust production will cease, the coma will disappear, and the object will transition back toward a dormant interstellar state. Its surface will gradually cool, and any remaining volatiles will freeze solid. In this sense, the passage of 3I Atlas through the solar system represents a brief and rare opportunity to study the composition, thermal behavior, and plasma interactions of an interstellar body that has remained inactive for millions of years. Another key objective is comparing 3I Atlas to other interstellar objects, particularly 1I Oumuamua and 2I Borisov. While Oumuamua showed unusual acceleration and morphology, Borisov resembled a typical comet with elevated CO production. 3I Atlas occupies a different region of parameter space, with extreme CO2 dominance, large grains, unusual polarization, and strong plasma interactions. This diversity suggests that interstellar objects may represent a wide spectrum of chemical and physical conditions. By studying 3I Atlas in detail, scientists can refine models of how interstellar comets form and evolve. For example, differences in volatile ratios reflect formation temperature and disk chemistry. Organic rich crusts suggest prolonged exposure to cosmic rays. Dust size distributions reflect internal cohesion and thermal history. Plasma interactions reflect the object's response to stellar environments. Understanding these factors helps construct a broader picture of planet formation across the galaxy. If CO2-rich interstellar comets are common, this implies that many planetary systems possess extensive cold regions where CO2 and CO dominate over water. This contrasts with the structure of our solar system and highlights the diversity of planetary architectures. Another important implication is how interstellar environments modify comet surfaces. Long-term exposure to cosmic rays likely plays a major role in shaping surface chemistry. The organic crust inferred from observations of 3I Atlas supports this interpretation. Studying such crusts offers insight into how cosmic radiation alters icy materials, potentially informing research into prebiotic chemistry. Post-perihelion observations may also help determine whether the nucleus of 3I Atlas has remained structurally intact. If fragmentation occurred but was masked by a dense coma, evidence may appear as the coma thins. Small companion fragments may reveal themselves as secondary brightness sources or faint diverging trails. Additionally, the tail morphology after perihelion may offer clues. If the ion tail reforms smoothly after the CME and remains stable as activity decreases, this suggests a relatively uniform plasma interaction. If the tail becomes irregular or disappears prematurely, this may indicate reduced ionization or changing solar wind conditions. As the object moves away from the Sun, long-term monitoring can also refine mass estimates. By analyzing the decline in activity and corresponding changes in non-gravitational acceleration, researchers can constrain the total volatile inventory. If CO2 emissions remain elevated longer than expected, this may suggest deeper reservoirs or internal stratification. Eventually, as activity ceases, the object will transition into deep space. At this stage, its surface will cool to interstellar equilibrium temperatures, and cosmic ray exposure will resume. Over millions of years, radiation processing will continue to alter the surface, potentially thickening or modifying the organic crust. The next stellar system it encounters may activate it again, repeating the cycle observed in our solar system. In summary, the long-term and post-perihelion evolution of 3I Atlas involves several key processes: decline of CO2-driven sublimation, potential activation of deeper ice layers, changes in dust size distribution, gradual relaxation of the plasma environment, evolution of rotation state, refinement of trajectory and mass estimates, and final transition back into interstellar dormancy. This phase completes the object's brief but valuable observational window. Data gathered during and after perihelion will provide essential constraints for building a unified physical model of the object and for understanding the diversity and evolution of interstellar materials. After reviewing all available data photometry, spectroscopy, polarimetry, plasma diagnostics, dust behavior, tail morphology, and solar wind interaction, an integrated physical model of 3I Atlas begins to emerge. This model does not rely on any single anomaly or observation, but instead synthesizes the combined evidence into a cohesive explanation consistent with known physical processes. The first major component of the model concerns composition. Every line of evidence points toward an object dominated by carbon dioxide rather than water. The CO2 on H2O ratio, estimated at roughly 8.1, lies far outside typical solar system comet distributions. This strongly suggests formation in an extremely cold region of its parent planetary system, where CO2 and CO freeze efficiently while water ice remains less abundant. Interstellar cosmic ray processing further enhances CO2 abundance, both through chemical conversion and through the formation of a dark, radiation-processed organic crust. This crust forms the second major component of the integrated model. Polarization data, infrared spectra, and dust size measurements all point toward a surface coated with large aggregates and complex organics. Such a crust influences thermal conductivity, suppressing water sublimation and enabling CO2 to dominate activity. It also explains the release of large dust grains, which in turn affect visibility, coma morphology, and scattering properties. The third component involves dust environment and radiative transfer effects. Large grain dominance produces a broad, diffuse inner coma with high optical depth. This smooths out brightness gradients and masks fine structure. Even if jets exist, they may remain invisible due to multiple scattering events inside the dust-dominated region. This effect is amplified by forward scattering geometry during specific observational windows. Radiative transfer modeling shows that a coma dominated by millimeter-scale aggregates can significantly reduce contrast, limiting the ability of high-resolution instruments to detect structural detail. This naturally explains why amateur long-exposure images, which integrate faint signals over time, sometimes reveal subtle features while spacecraft images do not. The fourth major component is the plasma environment. Strong CO2-driven outgassing produces large quantities of CO2+ and CO+ ions. These ions interact intensely with ultraviolet radiation and the solar wind, generating a dense plasma region around the nucleus. Plasma scattering combined with dust scattering can further obscure internal structure, creating the visibility paradox observed in early NASA imagery. Magnetic draping, charge exchange, and turbulence add further complexity. These processes create boundary layers, density gradients, and transient structures that influence both visibility and tail behavior. The ion tail responds rapidly to changing solar wind conditions, producing potential disconnection events, kinks, or sudden reorientations. The fifth component concerns rotation and internal dynamics. The absence of a clear rotational light curve suggests either tumbling or irregular active regions. If the nucleus rotates around multiple axes or undergoes torque-induced variations, the direction and strength of jets may change unpredictably. This produces inconsistent coma structures and complicates efforts to model internal activity. The sixth component involves thermal behavior and perihelion evolution. The insulating organic crust restricts the depth of heat penetration. CO2 sublimates readily, but deeper water ice remains inactive until the object reaches significantly higher temperatures. Depending on crust integrity, outbursts may occur due to subsurface pressure buildup. These events, if they occur, could temporarily improve visibility or release fine dust. The seventh component relates to solar storm sensitivity. CMEs and solar wind disturbances modify plasma density, alter magnetic fields, and change ionization rates. These external influences shape tail morphology, coma brightness, and scattering behavior. The predicted CME impact provides an opportunity to test the model. If visibility changes under altered plasma conditions, this will clarify which components dominate obscuration. By combining these components, a unified physical picture of 3I Atlas can be constructed. 1. Interstellar origin and cold formation environment. Chemical data indicate formation far from its parent star, likely in a region colder than the outer Kuiper belt, The extreme CO2 abundance and organic-rich crust reflect prolonged cosmic ray exposure and limited thermal processing. 2. Insulating surface layer radiation-processed organics create a cohesive crust that modulates sublimation, suppresses water release, and contributes to the dominance of large dust grains. 3. CO2-driven activity. CO2 sublimation begins earlier and remains dominant at larger heliocentric distances than water sublimation. This drives long-range mass loss and contributes to non-gravitational acceleration. 4. Large grain dust coma. Dust aggregates produce low-contrast brightness profiles and high optical depth. This obscures internal structure and reduces the effectiveness of short-exposure imaging. 5. Dense structured plasma envelope ionized CO2 and CO interact strongly with the solar wind, generating scattering, turbulence, and asymmetries. Plasma effects contribute to the visibility paradox and affect tail behavior. 6. Irregular or tumbling rotation state. Photometric inconsistency suggests complex rotation. This impacts jet geometry, torque balance, and activity variation. 7. Environmental sensitivity. Solar wind conditions and CME impacts significantly influence coma morphology and ion tail structure, making visibility and brightness highly variable. None of these components require exotic physics or artificial mechanisms. Each is supported by known processes and consistent with the behavior of natural interstellar materials. However, the anomalies become meaningful when considered together. Instead of representing a typical interstellar comet, 3I Atlas appears to be an outlier shaped by an extreme combination of factors: formation in an ultra-cold region, long-term exposure to cosmic rays, a dominant CO2 volatile inventory, unusual dust size distribution, dense plasma interactions, and a potentially unstable rotation state. This combination produces behavior rarely observed in solar system comets, explaining why 3I Atlas initially appeared anomalous. The integrated model also highlights areas where future observations can refine or challenge current interpretations. Multi-wavelength monitoring during CME impact will test plasma and scattering hypotheses. Polarimetric tracking may reveal rotation-driven changes in dust alignment. Infrared spectroscopy near and after perihelion may detect delayed activation of deeper layers. Tail morphology analysis can quantify magnetic and solar wind effects. High-cadence photometry may detect stabilization of the rotation state post-perihelion. Ultimately, the integrated model does not claim to explain every detail, but provides a coherent framework consistent with the majority of available data. It allows predictions about how 3I Atlas should behave under different conditions and identifies key diagnostic observations needed to confirm or refine the model. In this sense, 3I Atlas is not simply an anomaly, but an opportunity, a rare interstellar visitor that offers insight into how diverse planetary systems can be, how cosmic rays modify icy bodies over millions of years, and how extreme volatile distributions manifest under solar illumination. With an integrated physical model of 3I Atlas established, the next step is to examine its limitations and identify areas where existing data remain insufficient. While the combined evidence supports a natural and internally consistent interpretation of the object, several key uncertainties must be acknowledged. These uncertainties stem from observational constraints, incomplete datasets, and the inherent difficulty of studying an interstellar object with limited visibility and rapidly changing environmental conditions. The first major limitation involves direct nucleus characterization. The nucleus of 3I Atlas has not been resolved in any dataset. All estimates of its size, albedo, and surface structure rely on indirect inferences, brightness modeling, dust production rates, polarimetry, and spectral data. Without direct imaging, nucleus parameters remain uncertain to roughly a factor of 2 or more. This affects all downstream modeling, including mass estimates, torque calculations, and sublimation dynamics. A related uncertainty concerns the rotation state. Photometric attempts to derive a rotation period have produced conflicting results. If the object is tumbling or undergoing rapid spin state changes due to asymmetric outgassing, traditional photometry will not yield a stable periodicity. Without clarity on rotation, interpretations of jet geometry, dust dynamics, and internal stress remain speculative. Another significant uncertainty involves the depth and structure of the organic crust. While polarization and infrared data strongly suggest a radiation-processed surface layer, the thickness, porosity, and mechanical strength of this crust are unknown. These parameters influence how heat diffuses into deeper layers, how volatiles are released, and whether outbursts or fractures are likely. Without better constraints, predictions about perihelion or post-perihelion activity remain approximate. The volatile inventory also contains open questions. Although CO2 dominates observed emissions, the quantities of CO, CH4, NH3, and other volatiles remain poorly constrained. Low signal-to-noise ratios in the relevant spectral bands limit the precision of abundance estimates. As a result, some compositional interpretations depend on assumptions rather than direct detections. Determining whether deeper water ice will become active near perihelion requires more sensitive infrared data. The plasma environment represents another complex uncertainty. While multiple observations suggest dense plasma near the nucleus, these observations are indirect. Plasma densities are inferred from ultraviolet emissions, ion tail behavior, and radiative transfer modeling. Without in situ measurements, estimates of electron density, magnetic field structure, and turbulence levels carry considerable uncertainty. This affects interpretations of the visibility paradox and complicates predictions about CME interactions. Similarly, dust size distribution estimates rely on modeling of brightness profiles, thermal emissions, and polarization. While the dominance of large grains appears well supported, the exact distribution of grain sizes remains uncertain. This distribution affects both optical depth and coma morphology. If fine grain production increases near perihelion, visibility conditions could change significantly. Another source of uncertainty involves radiative transfer modeling. Multiple scattering simulations depend on assumptions about dust composition, porosity, and shape. If these assumptions deviate from reality, radiative transfer outcomes may misrepresent the true visibility of jets or internal structures. Although current models align with observations, a definitive conclusion requires more precise data on dust properties. The solar wind environment adds further variability. Solar wind conditions fluctuate on timescales from minutes to days, and predictions about CME arrival times and intensities carry margin of error. Because 3i Atlas appears highly sensitive to plasma conditions, small differences in solar wind parameters may produce disproportionately large changes in visibility and tail morphology. Despite these uncertainties, several targeted observational strategies can significantly reduce ambiguity and help validate or revise the integrated model. 1. High-cadence multi-wavelength monitoring during the CME impact. Coordinated UV, optical, IR, and radio observations before, during, and after the CME will reveal how plasma density, optical depth, and ionization respond. If visibility improves when plasma density decreases, this confirms plasma scattering contributions to the visibility paradox. 2. Post-perihelion infrared spectroscopy. Infrared data after perihelion can detect whether deeper volatile layers, such as water or CO, become active. This would clarify internal layering and thermal penetration depth, improving sublimation models. 3. Long-term rotation monitoring. High-cadence photometry across weeks may reveal stabilization of rotation or transition out of tumbling. A stable rotation period would allow mapping of active regions and improve torque modeling. 4. Polarimetric sequences across phase angles. Repeated polarization measurements can track dust alignment changes as the coma evolves and plasma density varies. This improves dust modeling and cross-validates coma structure interpretations. 5. Tail morphology tracking. Monitoring the ion tail for disconnection events, kinks, and orientation changes helps quantify magnetic interactions and solar wind influence. This provides constraints on local plasma conditions. 6. Detailed coma brightness modeling, using multiband photometry to track coma brightness over time, aids in assessing dust production rates, grain size evolution, and optical depth changes. This may help explain why some jet-like features appear intermittently in amateur images. 7. Radio dispersion measurements. Observing dispersion in OH and other radio emissions during plasma disturbances can provide indirect estimates of electron density near the comet. Collectively, these observations will help refine uncertainties and impose stronger constraints on the integrated model. A key question remains: what level of evidence is needed to resolve the visibility paradox definitively? The answer depends on isolating which component contributes most strongly: dust scattering, plasma scattering, or geometric effects. If high-resolution instruments observe the nucleus or clear inner coma structure after plasma density decreases, this strongly supports plasma-based obscuration. If such features remain hidden regardless of plasma conditions, dust dominance or intrinsic activity weakness may be the primary cause. Even if some uncertainties remain unresolved, the integrated model offers a coherent, physically plausible explanation for nearly all observed anomalies. More importantly, it highlights where additional data can refine the interpretation. Finally, placing 3I Atlas in the context of interstellar object science is essential. With only 3 confirmed interstellar visitors, including Oumuamua and Borisov, the sample remains too small for definitive statistical conclusions. However, the diversity already observed suggests that interstellar objects represent a wide range of formation environments, volatile inventories, and evolutionary histories. Studying 3I Atlas adds a critical data point to this growing field and expands our understanding of how planetary systems differ across the galaxy. In summary, although uncertainties remain in nucleus properties, rotation, crust structure, dust distribution, and plasma conditions, the integrated model provides a strong foundation for interpreting the object. The next observations, especially during and after the CME, will determine whether this model requires refinement or whether it successfully captures the essential physics governing the behavior of 3I Atlas. The investigation of 3I Atlas brings together diverse observational datasets, physical principles, and environmental interactions into a single scientific narrative. While individual measurements reveal unusual or unexpected behavior, the broader synthesis demonstrates that the object fits within the natural diversity of interstellar bodies. The anomalies do not contradict established physical laws. Instead, they highlight how different formation environments, evolutionary processes, and solar interactions can produce complex and sometimes counterintuitive observational signatures. The most defining characteristic of 3I Atlas is its extreme carbon dioxide-dominated composition. The CO2-H2O ratio, near 8:1, lies far outside the solar system distribution, but is consistent with formation in an ultra-cold region around another star. This highly volatile rich signature reflects the chemistry of its natal disk, where temperatures remained low enough for CO2 and CO to condense efficiently. Interstellar cosmic ray processing then altered the surface over millions of years, creating an organic-rich crust capable of reshaping thermal, optical, and sublimation behavior. This crust plays a central role in the object's distinctive observational profile. It suppresses water sublimation, promotes early CO2 activation, and generates large dust aggregates rather than fine grains. These large grains dominate scattering, reduce contrast, and produce a diffuse inner coma. Their presence strongly influences radiative transfer behavior, shaping the visibility paradox observed in high-resolution imagery. The plasma environment around the object adds another layer of complexity. Ionization of CO2 and CO yields dense regions of charged particles that interact with the solar wind. Magnetic draping, charge exchange, turbulence, and variable plasma density can all alter the appearance of the coma. The combined scattering of dust and plasma explains why some imaging systems detect structure while others do not. This interplay underscores the importance of understanding not only the intrinsic properties of the object, but also its dynamic environment. The rotation state of 3I Atlas remains uncertain. Photometric inconsistency suggests tumbling or irregular spin, likely driven by asymmetric outgassing. This affects jet geometry, dust trajectories, and non-gravitational acceleration. While the precise rotation remains unresolved, the behavior falls within the natural range observed in active comets. Thermal modeling reveals that perihelion evolution is dominated by CO2-driven sublimation. Deeper reservoirs of water may remain inactive if insulated by the crust. Outbursts may occur if pressure beneath the crust builds. The thermal wave's limited penetration depth makes post-perihelion behavior particularly informative, as delayed activation or changes in volatile mix may appear as the object cools. Solar-wind interactions, including the upcoming coronal mass ejection, provide a natural experiment to test multiple components of the integrated model. If plasma scattering is the primary cause of low visibility, the CME may temporarily reveal inner structures. If dust opacity is dominant, visibility may remain unchanged even as plasma density fluctuates. Either outcome will sharpen the interpretation. Taken together, the evidence supports a coherent physical interpretation. 3. Atlas is a natural interstellar comet-like object. Its unusual properties arise from cold formation, cosmic ray processing, CO2-driven activity, large-grain dust, dense plasma interactions, and complex rotation. No artificial or exotic mechanisms are required to explain the observations. Nonetheless, important questions remain. Direct imaging of the nucleus has not been achieved. The internal structure of the crust is unknown. Plasma density estimates rely on indirect inference. Dust size distributions, while constrained, lack precise measurement. These uncertainties reflect observational limitations rather than inconsistencies in the model. Future observations, especially around perihelion and during the CME interaction, will play a decisive role in refining the interpretation. Multi-wavelength datasets will allow scientists to track changes in volatile output, measure ion tail reconfiguration, detect any emergence of water-driven activity, monitor dust size evolution, and observe potential shifts in rotation or fragmentation. As more interstellar objects are discovered in the coming decades, the scientific community will gain additional examples for comparison. Early results already indicate that interstellar objects differ widely in volatile composition, dust structure, and physical behavior. 3I Atlas expands this diversity and reveals a class of objects shaped by cold disk chemistry and long-term interstellar radiation, while 1I Oumuamua challenged assumptions about shape and acceleration, and 2I Borisov resembled a typical comet with elevated CO. 3I Atlas introduces a new regime of CO2-dominant interstellar ice bodies. This diversity suggests that planetary systems across the galaxy produce a wide spectrum of icy materials under varying conditions. The broader scientific value of 3I Atlas lies not in its anomalies, but in the context it provides for interpreting interstellar processes. Its high CO2 content helps constrain models of chemical distribution in protoplanetary disks. Its organic crust provides insight into long-term radiation effects on icy bodies. Its plasma interactions demonstrate how interstellar objects respond to stellar environments unlike their native systems. Together, these characteristics contribute to a more comprehensive understanding of how planetary systems form, evolve, and exchange material across cosmic distances. The passage of 3I Atlas through the solar system is brief, but the data collected during this window will remain valuable for decades. The object's behavior under solar illumination provides empirical constraints for models of sublimation, physics, dust dynamics, plasma interaction, and radiative transfer under extreme compositional conditions. As observational techniques improve, researchers may revisit these data to refine theories of interstellar chemistry and small body evolution. In conclusion, the most consistent interpretation is that 3I Atlas represents an unusual but entirely natural interstellar object shaped by a combination of unique origin conditions and complex interactions with the solar environment. Its distinctive features: extreme CO2 abundance, organic rich crust, coarse dust environment, dense plasma interactions, and uncertain rotation do not contradict known physics. Instead, they expand the range of what is physically possible for icy bodies formed beyond our solar system. The visibility paradox, far from being a sign of artificial design, appears to be a product of radiative transfer effects, plasma scattering, grain size distribution, and geometric conditions. These mechanisms collectively obscure internal structure in certain wavelengths and viewing configurations, while allowing faint large-scale features to appear in long-exposure amateur imaging. The final assessment is clear. 3I Atlas is a natural object whose unusual behavior reflects the diversity of interstellar material, not a violation of physics and not evidence of engineered origin. Its study enhances scientific understanding of both cometary processes and interstellar chemistry, offering a rare opportunity to observe an object shaped by conditions far different from those in our own solar system.